Many people answer this question incorrectly the first time they hear it. I know I did. Here's the question. Can you use a list of cats where a list of animals is expected? I mean, if all cats are animals, shouldn't a list of cats also be a list of animals? What do you think? The answer, most of the time, is no. Why? This has to do with variance, and we'll get into the intuition in just a moment, but technically, it's because list is a generic or parametrically polymorphic type where the type parameter, t, is invariant. Let's take a step back and try a more intuitive example. If you ask me for a bag of fruits, and I give you a bag of apples, then you should be happy. You wanted a bag out of which you can take fruits, and I gave you a bag of apples out of which you can take apples. But since apples are fruit, all the things that you'll take out of the bag are also fruits. So I substituted what you actually asked me for with something that produces a more specific type, apples instead of fruit. This is the concept of covariance. Now, let's step to the other side, to contravariance. What's the intuition? If you ask me for a machine that can juice oranges, that can take oranges and make juice, but I give you a machine that can juice any fruit, then you should be happy. Since oranges are fruit, you can of course still put oranges into the machine, but I've given you a general machine so you can put any fruit into it. I substituted what you asked me for with something that accepts a more general type. This is contravariance. Let's look at the UML diagram. Variance regards how subtyping of types that use other types relate to the subtyping of the types that they use. Wow, that's a mouthful. Here's what I mean. Look at the red arrow in this UML diagram and in this UML diagram. Notice how they move in opposite directions. This black arrow is the regular is-a inheritance arrow, but this red arrow shows the subtyping relationship between the types that are used within these types. So fruit sequence here is a supertype of apple sequence. Apple sequence inherits from fruit sequence. Apple sequence is a subtype of fruit sequence. And fruit sequence, the supertype, has a method called next. And when you call next, you will get back something of type fruit. This means fruit sequence uses the type fruit. This is what we mean when we say uses. And the subtype of fruit sequence is apple sequence. But when you call the next method of apple sequence, you won't get something of type fruit, you will get something of type apple. But because apple is a fruit, not shown in this diagram, what you get back is you still get back a fruit. And the two arrows move in the same direction. This is covariance. Apple is a subtype of fruit, and apple sequence is a subtype of fruit sequence. So the subtype produces more specific output, apples instead of fruits. Let's move to the other side, to contravariance. Notice here how the arrows, the black arrow and the red arrow, move in different directions. So in contravariance, we reverse the subtyping order of the types that we use. So here we have a supertype called orange juicer, a machine that can juice oranges, and we have a subtype called fruit juicer. So orange juicer has a method called juice that takes something of type orange, that takes input of type orange, and it returns nothing. We imagine that what it does is that it juices this orange. Now the subtype fruit juicer also has a method called juice, but this method doesn't take objects of type orange, it takes objects of type fruit, a more general type. It still returns void, and this method overrides the other one. I forgot to say in the first case that, of course, the next method in apple sequence overrides the method in fruit sequence. And same thing here. The method juice in fruit juicer overrides the method juice in orange juicer. So the subtype accepts more general input than the supertype. And that means that the two arrows move in opposite directions. Fruit juicer is a subtype of orange juicer, but orange is a subtype of fruit, the other direction. So the more general type is found in the subtype. Whereas in the case of covariance, the more general type is found in the supertype. Let's define this more formally. Covariance means that if A is a subtype of B, then a type I that uses A is a subtype of a type I that uses B. Covariance: A on the left, B on the right. A on the left, B on the right. Contravariance, on the other hand. Contravariance means that if A is a subtype of B, then a type I that uses B is a subtype of a type I that uses A. It's reversed. We have A on the left and B on the right, and then B on the left and A on the right. Contravariance. In contravariance, the supertype of the contained type is found in the subtype. And remember, when we say is a subtype of, you can think of that as can be used instead of, is substitutable for, can substitute. A sequence that produces apples can be used wherever a sequence that produces fruits is expected. Covariance. In contrast to how a general fruit juicer can be used wherever an orange juicer is expected. Contravariance. So can you always use covariance and contravariance? No, not if you want to maintain type safety. In the beginning we mentioned that the generic type list is usually invariant in the type parameter. This means that it's neither covariant nor contravariant. It's invariant. Why is that? This is because generally covariance is only safe in output, while contravariance is only safe in input, type safe. And in the case of a list of type T, some unknown type T, that list, if it's read and write, can take objects of type T as input. You add items to the list. But it can also produce items of type T as output. You can read items from the list. So because it's both taking T as input and producing it as output, it cannot be either covariant nor contravariant, and hence it must be invariant. Another way to remember this rule is to consider what is known as the Robustness Principle. Be conservative in what you do and be liberal in what you accept from others. Be conservative in what you do and be liberal in what you accept from others. This means that if I am the subtype, I must, from my methods, return either items of the same type that my supertype is returning, or a subtype of those types, something more specific. That way, users of my type won't be surprised when they try to use this type as if it was an instance of the supertype. And on the contravariance side, be liberal in what you accept from others. That means that if I am the subtype, I must, from my methods, return objects of the same type as that which is returned from my supertype, or something more general, so that users of my type aren't surprised when they try to use me as if I was an instance of the supertype. So we have substitutability. Perhaps you're not convinced, so let's understand why this rule must be true to maintain type safety. Let's assume that it was possible to use a list of cats where a list of animals is expected. Covariance. Since the compile time type is list of animal, we expect that when we use the variable list, all items that we can get out of the list will be animals. And since the runtime type is a list of cat, our actual object is a list of cat, then indeed, all items that we get out will be cats, and since all cats are animals, this is fine. We will only get animals out. So since the type parameter is used as output, when we get items out, covariance is safe. But what about adding items into the list? Since the compile time type is list of animal, we must be able to add any animal, a dog or a duck, into this list. But since the runtime type is a list of cat, that means our object doesn't support ducks or dogs. It doesn't support all animals, and thus we will get a runtime error. So covariance is not safe if you want to use the contained type as input. Let's flip it around. Let's assume that it was possible to use a list of animal where a list of cat was expected. Contravariance. Since the compile time type is list of cat, we assume that we can put cats into this list. And since our runtime type is list of animal, something more general, then we can actually put any animal into this list. But since cats are animals, that also means that the object supports cats. So this is fine. If you're using the type parameter as input, then contravariance is safe. But what about getting objects out of the list? Since the compile time type is list of cat, we assume that all objects that we can get out of the list will always be cats. But the runtime type is list of animal, so there are no guarantees that this list only will contain cats. The list might contain dogs and ducks, and when we try to get them out and treat them as cats, we will get a runtime error. So contravariance is not safe if you want to use the contained type as output. If we want a list of cat to be a subtype of list of animal, then the type parameter must be covariant. But to maintain type safety, that would require the list to be a read-only list, a source. And the other way around doesn't work either. If we want list of animal to be a subtype of list of cat, then the type parameter must be contravariant. But to maintain type safety, that would require the list to be a write-only list, a sink. So because of this inevitability, most languages that support variance support contravariance in input and covariance in output. There are some exceptions, but in these languages you run the risk of runtime errors. So concretely, where can we use variance? There are three common ways. Number one, generics, also known as parametric polymorphism. In C#, for example, interfaces can be variant, and we denote the variance of type parameters using the in and out keyword, where in refers to contravariance and out refers to covariance, which should start to make sense now because of this rule of input and output. Second way, classes. Many languages support covariance and contravariance in classes. In C#, for example, you can actually write this code. You can have covariant return types. But in C# you can't have contravariant input. So you can't write this code using just classes, you have to use interfaces. But it depends on which language you're in. Third and last, functions. Languages where functions are first-class citizens, or where you have other facilities for passing around functions, like for example delegates in C#, in such languages you usually have support for variance. And then the case is quite clear. Functions can be contravariant in input and covariant in output. Contravariant in their parameter types and covariant in their return types. So in summary, here's what you need to remember. 1. Covariance allows a type to be replaced by a more specific type. 2. Contravariance allows a type to be replaced by a more general type. 3. Invariance means neither covariant nor contravariant. 4. Contravariance is safe in input and covariance is safe in output. Now that you have a good understanding of covariance and contravariance, you will have no problem understanding the Liskov substitution principle in great detail. Let me know if you want to talk more about variance and when it's useful. Subscribe! Yeah, that's too confusing.